Welcome to the Grandmaster Series. I'm your host, the sometimes unrealistic, but most certainly very real, Jim Scott. We will be speaking with the world's leading experts in data science and explore their approach for using natural language processing to analyze argumentative writing elements from students and identifying key phrases in patient notes from medical licensing exams. Pause for dramatic effect. I think we'll even learn a thing or two about DeBERTa. If you're interested in getting hands-on training to build text classification models, similar to what we're covering here today, you should sign up for our free self-paced course, Train a Text Classification Model Using Tau Toolkit. We'll have the link available in the summary below. Before we get started, there's just a few things I'd like to point out. Anything discussed which is publicly available, including links to relevant content, will be shared in the video summary below. And finally, please be sure to subscribe to our channel to be notified of upcoming videos in the Grandmaster series. Now, I'd like to introduce today's Grandmaster team. First, we have Chris Deotte, Senior Data Scientist at NVIDIA. Chris is a Ph.D. in computational science and mathematics with a thesis on optimizing parallel processing. Chris is a 4-time Kaggle Grandmaster. Next up, we have Dr. Christof Henkel, Ph.D. in mathematics with a focus on probability theory and stochastic processes, and is a senior deep learning scientist at NVIDIA. He's a 3x Kaggle Grandmaster. Next, Jean-Francois Puget. He holds a Ph.D. in machine learning and has published over 70 scientific papers in peer-reviewed conferences and journals. He's a 2x Kaggle Grandmaster. And last but not least, we have Ahmet Erdem. He's currently a senior data scientist at NVIDIA with a background in computer engineering and artificial intelligence. Today, Chris will be kicking us off for the presentation. I'll be back at the end to provide some closing commentary. Chris, it's all yours.
Great. Thank you, Jen, for the introduction. In today's episode, the Kaggle Grandmasters of NVIDIA will be discussing the Kaggle NLP natural language processing competitions of 2022. The KGMON that participated in these competitions are, and you'll recognize these names from Kaggle, CPMP, Dieter, Chris Deotte, and Ahmet. In today's show, we'll be looking at the competition feedback prize, evaluating student writing. This competition was aired 2 months ago and had over 2,000 teams. The KGMON and their teammates placed in positions 2nd, 3rd, and 7th. And all these positions were awarded part of the total $160,000 prize money. The second competition we'll be looking at today is the NBME Score Clinical Patients Note Competition. KGMON and their teammates placed in positions 2nd, 6th, and 20th, and positions 2nd and 6th won part of the $50,000 prize money. And this competition had around 1,500 teams enter. Before we jump into those solutions, just give you a quick overview of NLP. We're in a super exciting time in 2022. It's never been easier to build, train, and deploy NLP models. What's made it so easy is that as research papers develop new state-of-the-art models every few months, there are popular repositories that make these models available for download so anybody could use them. One of the most popular repositories is Hugging Face's repository. And on their repository, you can find the latest state-of-the-art models. And with just a few lines of code, you can download them. And what's even more powerful is that the models come pre-trained on billions of text, which means the models already come with lots of built-in intelligence. So all you have to do is train it a little bit longer on your specific task, and then voila, you have a language model. So you can see these easy steps here. So if you want to train an NLP model, you just pip install transformers. And then with these few lines of code from transformers, import your tokenizer, your model. Then you just instantiate the tokenizer in the model, and that downloads it from the repository. And then you're ready to go. You just convert your text into tokens. You build a task-specific head. You can train your model. And here are a list on the left of some of the pre-trained models you can download. And here's a little diagram. So what you download is the green rectangle. That's the transformer backbone. And then you end up building a custom head, which is the purple rectangle. And then you tokenize it and you train it on your specific task. And on the right, there's an example of a classification head. If your task is to maybe take sentences and classify the sentiment, maybe this sentence is positive sentiment, this sentence is negative sentiment. And on the left is an example of a question answer head where maybe your specific task is to search within text and find a span of text which represents the answer to a question. If you want to learn more about NLP overview, check out our episode 4 in the Grandmaster series titled Building World-Class NLP Models with Transformers and Hugging Face. And this includes more information about NLP history, RNNs and transformers, the innovation of attention in transformers, how models are pre-trained, and it lists a whole bunch of winning solutions from Kaggle's 2020 NLP competitions. All right, well, let's look at the 2 Kaggle competitions of 2022. First, we're going to discuss feedback prize, evaluating student writing. So in this competition, it was you were given essays from students grades 6 through 12, and they were argumentative essays. And our task was to find within the essays, we had to find different parts of the essay. So in this example, you see, for example, in blue, that's the essay's position. And then in light green, these are the essay's claims. And in the darker green, the essay's evidence. And then in the tan, the essay's concluding statement. So your model had to, given an essay, it had to both locate these spans and then also identify what type of class it is. And here's a summary of some of the features of the competition. So as I said, the task is to segment essays and classify into one of 7 rhetorical elements. I'll point out a particular challenge in this competition was the essays after tokenization. Over 40% of the essays were longer than 512 tokens. And this is significant because most of the traditional transformers you download can only handle sequence widths of 512 tokens. So this means you had to use other tricks, either a windowing trick, or you had to find models that could accommodate a longer token sequence length. The metric in this competition was macro F1 score on the average of the 7 classes. So if you know an F1 score, it is a formula based on true positives, false negatives, and false positives. And these were determined by looking at your span predicted, looking at the ground truth span. And if there's greater than a 50% overlap, then you have a true positive. If you predict something that doesn't overlap with the ground truth, that's a false positive. And then if you miss predicting something, that's a false negative. So then using these, you compute your macro F1 score. And I want to point out that human level performance would achieve 0.73. And what you'll see today is the majority of the models that we'll be presenting today, all of us score higher than 0.73, which means they were achieving better than human accuracy. So this is super exciting. And we're seeing this today in many fields with deep learning models, that they're actually beating humans in their respective fields. The data for this competition was we were given 16,000 train essays, and for for the prediction, we had to predict 10,000 test essays, whereas 39% were the public leaderboard and 61% were the private leaderboard. So the first solution we'll discuss today is my team's second place solution. It was I was part of a team of 3 people: myself, Chung Ming Lee, and Upav Bamba. We approached this challenge as a named entity recognition NER BIO NLP task. What this means is, ultimately we're given an essay and we have to identify, spans, which are pieces of the text. So what NER recognition is once you tokenize the text, you could think of that as, basically breaking into individual words. Tokens and words aren't exactly the same. And then for each word, we assign it one of 15 labels. So it's we either identify it as the first word in one of the 7 classes. We identify it, that's the B label. We identify it as a word that falls in the middle of one of the spans, that's the I label, or we say the word is not part of any of the classes, and that's the O label. So that's 15 classes. So each word is sort of classified, each token is classified separately. And the key parts of our solution are 3, which is we used 10 diverse backbones trained on a 10-fold CV. Then each backbone made token level predictions, and then we just averaged those together. And then the next key part was we converted the token level predictions and we created spans out of those via post-processing. So then for each of the 10 models, we had a set of spans for each class. And then finally, we used weighted box fusion to combine the spans of different models. So here are the 10 diverse backbones that we used. You can see the list here. You can see that the top 5 are a new state-of-the-art model called DeBERTa. We used a few varieties. We used the original version, the version 2, the version 3, and we used sizes large and extra large. We also used the long-former large model. We took a RoBERTa model and we converted that into a model that can handle longer token input sequence lengths. We also used the funnel transformer, the Big Bird RoBERTa base, and the Yoso model. So what was special about all of these models, in addition to being huge diversity, they each have a huge variety of different types of pre-training, which means that they each have a huge contribution. They use different vocabularies. But in addition to all the diversity, what made them all special was each one of these can actually handle input out of the box. They can handle input lengths larger than the typical 512. So all of our models we trained on the full essay, which was we used a sequence length of 1,536. So we didn't need to use windowing techniques or anything like that. We just pushed the entire essay into the transformer and trained it from there. So each model outputted prediction for each token. And for the purposes of discussion, we could just roughly call a token a word, right? So each model is basically making a prediction for each word in the essay, roughly saying which classes it belonged to. But what we need to do is we need to combine those word predictions and actually get, a whole clause, a whole group of words called a span. And this is where post-processing comes in. And it's the process of converting. So the first rule that we sort of had was we repaired spans. So for instance, if you had 10 consecutive words and word 1, 2, 3, 4 were predicted to be part of the conclusion, let's say word 5 was not, and then words 6, 7, 8, 9, 10 were part of the conclusion, you could roughly say, wait a second, it looks like we sort of have a whole group going here, but there was one word that was wrong. So we sort of repair spans is that if we see a word among a larger span that doesn't match everybody else, we just change that prediction to conclusion and then say the whole group of 10 words is that span is a concluding statement. And we did other tricks like that. Essentially, the goal is to kind of get the longest continuous spans you can. Next, there's some general rules you can apply. So the concluding statement, for example, usually came towards, well, it comes towards the end of the essay. So if the model is predicting a concluding statement in the beginning of the essay, we could remove that. We also noted sometimes with the rebuttal predictions, those spans, there'd be a bunch of them, but we noticed that if you just kind of clump them into one span, that improved the CV and LB score. And then lastly, you can analyze what are the expected lengths, right? So evidence was generally around maybe 45 tokens long. So if our model predicted, an evidence span that was shorter, say 30 tokens, well, we would just extend it and make it longer. And this improved the CV and LB score. All right, so after applying post-process, then each model's individual token predictions are now converted into span predictions. And here's what that looks like. So in the middle of this slide, you can see model 1. So each one of these letters, imagine is a token, or imagine it's a word in the text. And imagine we have 3 classes, class A, B, and C. So model 1 is predicting that those 4 green words are part of the B class. And model 2 has different predictions. Given these 8 words or tokens, model 2 is predicting that tokens 2, 3, 4, 5 are part of the B class. So the post-processing took these 4 Bs and turned it into a length 4 span. Now, we somehow have to combine these 2 models. So they made different predictions. We somehow have to combine these 2 models and just make one prediction. So a common approach is just to average, the token probabilities. But if you did that, you may get something like the intersection of the spans, which, there's a very strong agreement for those middle 2 tokens. So if you simply average the 2 predictions, you may just predict that the 2 middle tokens are B. Now, what weighted box fusion does is weighted box fusion, it looks at the 2 spans and it finds the start of each span and then the position of the start. And then it takes the average position. And then it looks at the 2 ends and it takes the average of the 2 end positions. And that's represented in the bottom picture here, where you can see if you were to apply that, then the weighted box fusion would predict 4 Bs. So you can see that weighted box fusion, it sort of preserves the length of the spans, and it sort of intuitively makes sense that if someone predicted a span here and someone predicted a span further to the right, we should predict the span somewhere in the middle. So this technique is frequently used in computer vision. It was prior to this competition, I haven't seen any examples of it used in NLP, but it was a huge powerhouse. I mean, this allowed us to take our 10 diverse models and then we just put them all into the WBF algorithm, and then out came, just one set of predictions. And as you can see, it jumped our team's F1 score to 0.74, finishing in second place. So weighted box fusion was extremely powerful in this competition. And that is the summary of our solution. So next, Ahmet will be discussing his team's third place solution.
Thanks, Chris. Hi, everyone. As Chris said, I will be sharing our third place solution. So we also had a team of 3, like Chris' team, and we had a close fight on leaderboard, and I will be presenting this. Next, please. So you see our pipeline on the slide. So I will briefly explain it. Same as other teams, we used pre-trained language models. And with sliding window approach, we could actually use any kind of backbone with any kind of maximum token length. And we also use 2 layers of GRU on top of these transformers to make the predictions more continuous because we are segmenting them actually. And random mask and cut mix augmentations are used to reduce overfitting. During inference, texts with similar token lengths are kept together to avoid inefficiency. This is another trick we applied. And in this problem, we use language models, and they make predictions for each token, right? And but the goal is to predict sequences. Therefore, we generated sequence candidates from model output using a small set of rules. And you see some example candidates on the screen. And with the rules, models determines the start place, and then it generates all possible sequences until some endpoint. Next, please. And while generating these sequences, we also extracted some features like length of sequence. You see a lot of features here, like 12 set of features, and in total this is like 30 features. And the main first place solution is actually very similar to ours, if I remember it correct. And in first place solution, the main difference, as far as I remember, is they had 5 or 10 times more features than us. But we had some like 30 or around 30 features, which are mostly token probability statistics, as you can see on the slides. Next, please. All experiments are done using XGBoost on GPU, since it is super fast. And we also use LightGBM on Dart mode. Dart mode randomly drops trees, therefore it is more robust. This is the reason we added it as a second model. But it was very slow for training and inference. For training, it's okay, but for inference, we had limited time, and we wanted to use more language models in this limited time. Therefore, we used Rapid's Forest inference library, and it significantly improved our inference time. And we didn't waste a lot of time on 3 models, and we could add more language models to our ensemble. We also use different thresholds and features for each discourse type. So we behaved as if they're all different problems. And at the end, candidate sequences are sorted by model predictions, and the most confident ones are assigned first. 20% overlap between sequences are allowed. And this is how we generate the final discourse labels. Yeah, this is our solution. Let's continue with Christof's solution.
Yeah, thanks. So I will present my team solution, which consisted of Darag, Pascal, and myself. We finished on 7th place. Next, please. As opposed to biotagging, as most participants did, we used an 8+1 model output, meaning that we directly modeled the 7 classes plus an additional class if there's no span to predict. And we trained this with a cross entropy loss. And then we had one more model output, which basically says if a new span is starting or not. And this was trained with a binary cross entropy loss. Our final solution is an ensemble of several models, which were specifically optimized for handling long sequences. As such, we had BigBird, Longformer, DeBERTa, DeBERTa v2, DeBERTa v3, and BART. We found that using a max size of 1250 tokens is a good trade-off between accuracy and speed. And for the shorter model, in this case BART, which originally only has 512 tokens at max, we extended the position token length by repeating the position embeddings until we reach 1250 tokens. We assembled simply by a weighted average of word logits, where the word logits have been derived from token logits by mean aggregation. And we used Optuna to tune ensemble weights and post-processing hyperparameters, where the post-processing is similar to what Chris and Ahmed has done. In total, I would say our solutions is a bit more simple than the ones presented, simply due to the fact that we missed improvement by feature engineering plus stacking or weighted boxes fusion. Next one, please. So as you can see from the 3 top solutions presented, DeBERTa seems to be the new state-of-the-art model used in NLP downstreaming tasks. So what I want to do here is to discuss a little bit more in detail where the main difference between DeBERTa and the other model is, and why DeBERTa is so much more powerful. So DeBERTa stands for Decoding Enhanced BERT with Disentangled Intention. It comes in 3 versions, as we saw in the top solutions. And in the very first version, there were 2 novel techniques introduced. The first one is Disentangled Attention Mechanism. So in contrast to BERT, where the content embedding and the position embedding is summed into a single vector which represents each token, and then those single vectors are used to calculate attention between tokens. In contrast to that, in DeBERTa, each word is represented using 2 vectors that encoding content and position separately, and the attention weights amongst words are computing using disentangled matrices. So there's not one attention weight, but in fact there are multiple attention weights for a word pair. As you can see in the formula, the final attention weight is the sum of 3 individual attention weights, where the 3 individual attention weights are at first the content-to-content attention, so attention between the content-to-content vector, then a content-to-position attention, and then a position-to-content attention. So to say it more frankly, the attention is separated into 3 different parts compared to BERT, and this enables a more sophisticated modeling of position and content relationship, which makes DeBERTa really powerful. The second improvement is an enhanced mask decoder. So instead of using the position embedding only in the very first layer, as it is done in BERT, in DeBERTa, the position embedding is fed into every decoding layer to predict the mask tokens in the model pre-training. Next slide, please. Yeah, but people didn't stop with version 1. They saw there are more improvements possible. And although DeBERTa V1 was already beating BERT and other transformers, they looked into further improvements. So they published version 2, which added improvements to the tokenizer and to the position encoding. Firstly, they changed the vocabulary and used a larger vocabulary of size 128,000 built from the training data, and switched from GPT-2-based tokenizer to a sentence piece-based tokenizer. Secondly, they used n-gram-induced input encoding, where an additional convolution aside with the first transformer layer is used to better learn the local dependency of input tokens. Additionally, they focused on improving the computational efficiency, for example, by parameter sharing of projecting matrices in the attention layer. And they also improved the encoding of relative positions by bucketing similar relative positions. But that was not the end of the story. They came up with version 3, where they focused on improvements to the training objective, because they saw from other language models that there different training objectives might very well improve the model and the respective downstreaming tasks. So what they did was that they replaced the masked language modeling objective, which they used originally in DeBERTa, with the replaced token detection objective, originated from Electra model. In the replaced token detection, the model not only need to find out the true token for a masked token, but in contrast to that, randomly tokens are replaced with fake tokens, and the model need to find out which tokens are fake and what is the true token to be at this position. And since this task is much more difficult, it also improves the, let's say, intelligence of the model and helps for better accuracy in downstreaming tasks. So as you can see, to sum it up, DeBERTa is not only a single improvement compared to BERT, but it's a list of several improvements coming in different versions that helps making DeBERTa the new state of the art for NLP modeling. Next one. And with this, I give over to Jean-François, who will discuss his solution for the NBME competition.
Thank you, Christof. All right. So this competition was NBME stands for National Board of Medical Examiners in the US. So part of the exam to become a medical doctor in the US, people have to assess and diagnose someone. So there are trained people who act as if they had one of several predefined cases. And the potential doctor must look at the person, ask question, whatever, and write a report, a medical note. And then examiners must look at the notes and check if the candidate has identified all the things that he was or she was supposed to identify. So what we are given are these notes written by candidates. They are called patient history note. And we also have a list of features that the candidate must identify. So for each feature that should be identified and for each note, we have an annotation of where the feature is identified in the note, or no annotation if it was not identified. And we are asked to train a model to check if features are identified and where in the note. So the ground truth, what we have to train, we were given 14 plus 1,000 nodes feature pair. So for each feature, we had 10 nodes, if I remember well, or 100, sorry, I don't remember. But this is small data for these big models. So they also gave us 10 times more data, where clinical notes, patient history notes, without annotation, but we know which feature might appear in each of these. So we have more data without the annotation, which the host explicitly said you can use semi-supervised or unsupervised techniques, and we did. So next, please. Here is an example of what one training example looks like. So the feature is called early awakening. So for each feature has a little phrase or sentence describing it. And here you have an example of an actual patient history note. And you see the green piece is where the feature is identified. So waking up early. So waking up early is, in a way, the answer to where does the feature early awakening appear. But if you look, there is the next few words are 4-5 a.m. So if you read in a piece, the green and blue, you have waking up early, 4-5 a.m. This could be also an answer. So from a layman point of view, like me, in many cases, the proposed answer could be a bit different and still look as good. So the annotation, so the selected answer, is a bit noisy. And there are other examples where the answer is repeated and only some of the occurrences were identified as the answer and some were not. Anyway, so it's an interesting and useful NLP challenge. Next, please. And I was a bit lucky. Well, I worked, but there is always a bit of luck in the result to finish second solo. I don't recommend to do too much solo competitions. It's very stressing. But when it works, it's really good. Next, please. Not surprisingly, after what Christof said, so looking at previous competition, like the feedback that we discussed right before, I started with DeBERTa and different versions. So I ended up with DeBERTa and DeBERTa v3. Remember, the difference between DeBERTa v2 and v3 is just a training objective. So DeBERTa v3 looks a bit better, and it's the same model using PyTorch and Hugging Face Hub. One thing I did, apparently I was the only one doing it, I pre-trained further the model on a data set called Squad v2, which is a question answering data set prepared by Stanford University. And the reason is, so even if DeBERTa is a great model, here we have a specific problem, which is given a context, a patient note, and a question, the symptom, where does the answer of the question appear in the text? And this is a well-known task in NLP research called question answering. And Squad v2 is a gold, or used to be the gold standard for this kind of question answering, where we have to predict the span. So we have to predict where the answer appears. So I pre-trained on Squad v2, the two models. I use A100 for the first time on this competition. These rocks. A100 are at least 2 times faster than the previous generation GPU for these models. And it's really fast, 5 minutes for the base model, 12, I will explain why. The architecture, so we don't use a model as is. As was shown before, it's customary to add specific heads to capture the specifics of the task. So here I use 3 heads, which are a bit similar to what Christof used in the previous competition. The main head is a token classification. Is the token part of the answer or not? And the other 2 predict if the token is the start of an answer or if the token is the end of an answer. I didn't use those 2 start-end prediction for the final prediction, but having them as auxiliary loss improved the accuracy of the model. Then I use a number of tricks or architecture piece to add regularization to the model to avoid overfitting. Remember, the training data is really small for these large models. So one that is quite classical is these transformers are like a sandwich with layers, with attention and MLP, and then you repeat. So in DeBERTa large, it's 24 layers. So after each layer, you have a representation of the token, an embedding. usually people take the last one to make the prediction. You can combine all the layers, and it helps a bit. So you just learn coefficient to combine the layers and use the weighted sum of the layers as your basis for classification. I keep the sum of the coefficient to be 1 so that I don't change the scale of embeddings. The other thing that several teams did, it looks like the truth. So the answer being selected or not depends on its location in the text. So if there are repeats, the first one is more likely, apparently. So to capture the sequence dependence truth, I added the RNN on top of DeBERTa. A simple one, single layer, but it helped a bit. And then last trick, dropout is a very effective way to fight overfitting in deep learning. Someone published a paper recently showing that using 5 levels of dropout in parallel was further improving, so I used it as well. The last component, so that was the architecture. Then training a model upfront like this alone could be in the top 50. And then to move to the top, I use pseudo labeling. So I won't explain what it is because Chris will have a very nice explanation in a few minutes. Next slide, please. So data processing, text processing. My advice is with this model, they are so good now, the tokenizer plus the model are so good that the less pre-processing, the better. Still, there was just a little, the patient notes came sometimes in full uppercase, sometimes in lowercase, sometimes in mix, but there was no semantics. So I tried all lowercase, it was much better. I stick to it. Then there are also medical abbreviations, and you see some example, FHX, which means family history, etc. SHX, social history. These are unknown to a generic model like DeBERTa. So the hope is the model will recognize this and learn, but the training data is so small that I was not sure. So I tried to group together abbreviation that have the same semantic meaning, like FHX and FH. Adding so why do I add a white space is to keep the same length. So remember, we have to predict spans, so character position of the answer. So if you change the text and you shift characters, you have to maintain the shift and be able to undo it after the model prediction, which could be quite complex. And in the limited time of a competition, I thought it was too risky. Other people have introduced additional tokens, which looked powerful. I tried, but I did it wrong, so it was not useful. Post-processing, same story. The less post-processing, the better, in my view. Some teams have pages long of post-processing. If there is a pattern, the model should learn it. That's my view. Except if the pattern cannot be learned via tokens. So here are examples. If the boundary of the answer lies within a token, there is no way the model can learn. So there are several examples. DeBERTa is great, but it groups all spaces before a word in the first token of the word. So if the boundary is after the space, right at the beginning of the word, the model cannot know. So it will predict that the space is part of the answer and you have to remove it. Another example, which was a bit more tricky, you see abbreviation like 17-year-old female written like 17YOF, just in one word. When it is tokenized, the OF is tokenized with of, the word of, which is common in English. But in fact, the boundary, if the feature is about the age, The answer is 17-year-old, so it should be 17YO. The limit is right in the middle of. And if the feature is about gender, the answer would be the F and not OF. So depending on what the feature is, I split the answer in the middle of the OF token. But this really brings, it's not materially significant. The other two are significant in the leaderboard. Next, please. All right. And then ensembling was quite simple. I used variants of the model. So remember, I used DeBERTa v3, so that's 2 backbone. I use the RNN, so it's easy to choose between LSTM and GRU, so that's again 2. And then I trained the model either on 4 folds to do cross-validation, and in the end, I retrained 4 times on the full data. So this gives me 32 different checkpoints, and I just blended the probabilities and thresholded them. So very simple. I'm afraid of overfitting because the data was too small. When you have more data, you can do stacking, what have you, but here I was cautious. And that's, so my solution is not fancy, it's robust, I would say. And with this, I will let Christof present his solution.
Yeah, I will talk about the 6th place solutions, where I participated in the same team as in the feedback competition, namely with Dark and Pascal. Next, please. And same as with Jean-François, we have a very simple but robust solution, which we think was quite important for this competition. The key ingredient was an ensemble of different DeBERTas. We tried other backbones than DeBERTa, such as BioBERT or RoBERTa or something, but DeBERTa was so much more powerful that the weaker models won't even benefit in an ensemble. The key workflow we have is a 2-stage approach, where we utilize knowledge distillation and language model pre-training on the unlabeled data. So I call the labeled training data, I call train.csv because we saved in a train CSV file, and the unlabeled data I will call extra.csv when I go through the illustration you can see here. So our models for the first stage were 4 models, namely DeBERTa, DeBERTa v2 x large, DeBERTa v2 xx large, and DeBERTa v3. Each of those models we train on the given train.csv, which only takes a few minutes, and then we do inference on the extra unlabeled data to generate pseudo labels for this data. Chris will discuss pseudo labeling in more detail, but first just think of it, we label the unlabeled data with models trained on our original train data. This generates a labeled version of the extra data, which I call pseudo 1, 2, 3, 4 in the illustration. And then we simply ensemble our 4 pseudo predictions into one master pseudo.csv file, which we keep on the side. And then in the second stage, we train 3 models, namely DeBERTa large, v2x large, and v3 large. As you can see, we didn't use v2xx large because it was too large for the inference kernel used in the Kaggle environment. So restricted to 3 models which we can use. In the first step, we pre-trained those 3 models using masked language modeling objective on the given extra data to basically learn a little bit more the domain vocabulary contained in the extra data. And then we trained on the training data plus the pseudo labeled data we kept from before. which increased the training data amount by 10x, I would say. And also increased the training time needed by 10x. But that really helped to improve the model accuracy, and also was a way to distill dV to XX large, which was part of the first stage, but not part of the second stage. And then the models, the weights coming out from this step were used to infer on the given test data, which then again assembled to our final test predictions. And with this rather simple workflow, we finished 6th place in total. And with this, I would give back to Chris, who will present his solution.
Thanks. So I'd like to present our team's 20th place solution. So unfortunately, on the public leaderboard, we were in the gold 9th place. Unfortunately, when they revealed the private leaderboard, you can see we dropped 11 places to 20th. But you can see with the scores here, they're very, very close, right? So basically differences in the 4th decimal place move you up and down. Our team consisted of 4 people. It was myself, Theo, Mintrifam, and Hasuki. And I'm just going to highlight 2 things about our solution. But first, I got to highlight a unique things about the competition. So as was previously said by JFP and Christof, it was interesting. So the competition gave you some labeled data, but it also gave you a lot of unlabeled data. And I think there was 1,000 train notes that were labeled, and there was 39,000 that were unlabeled. So this is all this text, but there's no labels, right? So you can't train with it immediately. You have to figure out how to use it. So that was unique. And then additionally, the metric was F1 score, but it was per character. So this is interesting also because models generally work with tokens. So the two strengths of our solution sort of address these 2 points. Basically, how do you use the unlabeled data, and how do you make sure that you're optimizing for a character level F1? So I want to show this diagram here. This was made by my teammate Theo. This was a diagram for one of the models that he built, and I think this is really neat. So people frequently on Kaggle, ask how do you do pseudo labeling, and how do you compute CV with pseudo labeling? And it's actually very tricky because you have to be very careful if you actually want to make a meaningful CV score and have it leak free. And let me explain. So typically people generally will do a 5-fold CV, right? So that amounts to, you train a model on, say, folds 3 to 4, then you predict the unseen you train on folds 0 to 3, and then you predict the unseen fold 4, and then you do this, and then you train on 4 different ones and predict on fold 0, etc. And then you can compute a CV score. And that's the sort of top left of this diagram. Well, if you want to do leak-free pseudo labeling, what you need to do is when you train fold 0, 1, 2, 3, that's one model, that's one model. So using that model, you can make predictions on all of the 39,000 unlabeled train data. And then all of a sudden you have labels. Those are called pseudo labels. They're not necessarily the truth, but it's, you added it yourself. So you keep that, you put that one set aside, and now your CV was 5 folds, right? So then you train your model on using folds 1, 2, 3, 4, and you use that model, and you pseudo label the unlabeled, and that's a second set. You put that aside. So you do this for each of your 5 folds, and you have 5 different set of pseudo labels. So then in the second stage, which is the second row of this diagram labeled model 1, you can now train a new model again. And then this time, when you're training folds 0, 1, 2, 3, you can actually use the first set of pseudo labels that you made using fold 0, 1, 2, 3, and you just add that to the training data, and you train with that, and then you predict fold 4. And if you notice, it's leak free because that pseudo labeling never included targets from fold 4. So when you predict you're out of fold 4, there's no leaks. And then in your 5-fold CV, you do it with you then train on the next set of 4 folds, use the next set of pseudo labels, etc. And you can see in the diagram, so the first row is the first model without pseudo labeling, had CV 884, public leaderboard 884, and private leaderboard 888. Then once we incorporate one iteration of pseudo labeling, the CV jumps up to 889. It's now utilizing information from the unlabeled data, and it has a public leaderboard of 889 and a private of 891. Once again, we create pseudo labels, and then we use this another time to make another model. This model has CV 892, public 892, and private 892. Now, these leaderboard scores I'm reporting are just truncated. So actually, in this example, this specific single model using DeBERTa, DeBERTa large, may have been a V3. Yeah, DeBERTa large V3. That private leaderboard was actually 0.8929. So this single triple 3-stage pseudo-label model would actually, you could see, been a gold level model. So the process of pseudo labeling is very powerful. DeBERTa is very powerful. Our final solution was an ensemble, which scored slightly less than that one. So I thought that was neat. That's how you do a leak 3 pseudo labeling. And then just to also mention, a key element of our solution was, as JFP pointed out, when a model makes a prediction on a token, the DeBERTa tokenizer will include the space character in the beginning of each token. So, but if you're predicting the spans, you don't want to include that space in the very beginning. So you had to sort of use a post process to remove that. And we removed those spaces. That gives a boost of 0.002 or 0.003, which is pretty strong. So that's a summary of our solution.
All right. Chris, Christof, Jean-Francois, Amet, thank you all very much for spending your time speaking with myself and all the viewers today. The use of DeBERTa for natural language processing seems thoroughly convincing and sounds quite promising. As I mentioned at the top, if you're interested in getting hands-on training to build text classification models similar to what we've covered here today, please sign up for the free self-paced course, Training a Text Classification Model using Tau Toolkit. You can find the link in the summary below. To all the viewers, thank you so much for spending part of your day with us and taking the time out of your otherwise busy schedule to enjoy this episode in the Grandmaster Series. I'll leave you with this quote. The most basic of all human needs is the need to understand and be understood. The best way to understand people is to listen to them. Pause for dramatic effect. If, like me, you don't have time to listen or read everything ever written, well, use natural language processing to your advantage. I'm Jim Scott. Have a great day, and may all your computing be accelerated.